Chairman.
Chairman? That's another one. Yeah.
Yeah, why not?
Why do I do it?
Let me announce you to people.
It pays €1,000. Keep in mind.
Everybody talks as well. Coming this morning, ladies and gentlemen. I want to introduce this great guy who I'm sure is going to entertain us and educate us with quantum particle light clock or heavy beatbox. So a round of applause, please. Go on.
Thank you so much, Lynn. I'm Martin van der Mark. I work at Philips Research in Eindhoven in the Netherlands. I spent my time working on optics of whatever kind and have been for a long time. I'm a physicist by training, both theoretical and an experimental physicist. So, for fun, I try to uncover the foundations of physics. And this is also the reason why I'm here. And together with John, we've been working for 27 and a bit years on all sorts of things. And this is in one way or another related to it. And as a matter of fact, it's about harmony, superposition and mixing of a light wave in a cavity. Now, light waves in cavity, for a laser physicist like me, it is a piece of cake you would think. Well, we'll see. So what does this microscopic classical system tell us about the structure of a relativistic quantum particle? Because that's actually where I want to end up, one way or another. So the outline is as follows. First I tell you about the matter of mass. How heavy is light? Then on the beat of the light clock. Then a part that is about the relativistic matter about the quantum particle. And then some conclusions. And the aim of this project is to find appropriate boundary conditions to describe elementary particles with a parametric nonlinear theory of topological electromagnetism. And of course this is what I'm actually doing it for. So this theory is there. I presented it 2 years ago in San Diego at Optics and Photonics. And the differential equation is nice. A set of differential equations is even better, in particular when they look very much like Maxwell's equations. But of course you need boundary conditions, otherwise you cannot find solutions. And the more you know about the solutions you want to obtain, the more chance you have that you actually get something out. So, first part, on all that is heavy. Now, how to weigh an object? First we have to learn how to weigh an object. So I teach you a bit here. So to correctly determine the gravitational mass of an object, one needs the following. You can see it, a balance to make the measurement independent of the gravitational constant of the planet you're on. A heavy pair of scales rather than very light ones, because there are always thermal fluctuations and stuff, so you want to sort of average that out, so that makes it that it's a low pass filter. And you rather want to do this in a vacuum. So doing this on the moon is actually easier than doing this on Earth. Or what you could do, for practical purposes, have equal boxes so that the buoyancy of whatever you put on there is the same on each side. And then you can go into more details, because weighing properly is actually even harder than this. But this is the basic idea of what you're doing, and for the purposes of today, this is enough. So, now, if this box that you put around it is actually opaque, you cannot actually know whether you're measuring lead or wool, as is apparent in this case, or perhaps a gas, like air or a vacuum over there. So, you can't see it, so you have to determine that from what you see in the measurement. And you can't, and that's a thing that I will try to point out. So, suppose that you wanted to measure the weight of a gas. So you put some gas in the box, and it will certainly have a certain weight. This is nothing that you put there, so you weigh that. It works. We all know that, or should know that. And but how does it actually work? Well, there's a pressure of the gas down on the bottom of the box, and there's also a pressure on the top of the box, but there's a difference in pressure between the top and the bottom of the box. And if you work that out, and you can follow the equations there, it is a bit of, I don't go to bother about that. You can find this in the paper called Light is Heavy, that I published a long time ago, but it's on the web. You can find it. You can find all my papers on ResearchGate. And there's a link in the abstract that I put in this conference, so you can immediately get there, or do everything. So you find this. You look at the barometric pressure difference between this and this, and you see the constant there is 8,572 meters. That's like Mount Everest close by. But you can put the ideal gas law in, and then you find immediately the right answer. In practice, it's a little bit more complicated, of course. Gases do not have to be ideal, but still, whatever you do, it will come out. Then you will weigh this gas, exactly what it, the amount that it is. There's a joke or a riddle that you often find. It says this guy comes to Briggs and he has this truck, and the truck weighs 1 ton. And it has a cargo of 2 tons of chicken. And the sign on the bridge says no more than 2 tons. So the total weight is 3 tons. So he can't cross the bridge, but he knows, but my truck is only 1 ton. So he gets out of the truck and he bangs on the side of the truck, and all the chicken, they fly up, you know, and he very rapidly crosses the bridge. So what happens? Well, he falls through the bridge because it is still 3 tons. So the downward flow of the air, of the chicken flying, is of course the same weight. So whatever you put in a box, the weight of that is in there. The energy of that is in there. That's actually really the thing. So now we can do a gas molecule, just a single one, which is a little bit different because now we don't have the pressure of the average of the whole collection, where molecules in between sort of bounce off each other. No, now we have a single one that goes from the bottom to the top and so on. And it's the same thing, so the molecule is decelerated when it goes upward, it's accelerated when it goes downward.
The only thing is you have to replace the 16-ton weight on the right.
Yeah, the 60 ton is a bit much, but I always like to stick to known numbers. This number is from Monty Python, I think. So this is a known number.
Your method have a problem because you assume there's no repulse gravitation. If there's repulse gravitation, your method won't work.
Questions for later, please. So again, if you look at the change in momentum, so you look at you have the momentum change here and there, and you subtract those, then that momentum change is written over there. And then if you take, you do dp by dt, then you have the force. So if you do the velocity, the velocity by dt is of course the acceleration. And then, of course, you end up with F is exactly mg in that case. So the single molecule is weighed this way as well. But indeed, you need the heavy scales because this is the thing that bounces up and down, and it does this. So the low-pass filter of the scales here has to be such that they're slower than how fast this is. For a real experiment, this would certainly work. So, because this is quite a fast motion, of course. Now, molecular gases find photon gases. It's the same thing. It's the same thing. So you have a photon that is in a reflecting box, and it is going up and down in there. It might be going like this, maybe going in whatever path. Again, a momentum change on the top and the bottom. A blue shift when the gravitational blue shift of the photon when it goes down, gravitational redshift when it goes up, and therefore those are different, and you can work it out again. So the gravitational redshift, you can look it up. You can also do it slightly more cleverly in special relativity, which I did in the paper Light is Heavy, so you don't need any general relativity to come with this answer. And you get exactly to that the mass of the photon in the box is P over C. So, yeah, now you say, what's that? Some people say, this is ludicrous, because I am saying light is heavy. Well, how light is light, you can say. If it has a rest mass of m0, the scaling is as follows, of course. The mass is gamma m0, and gamma is, of course, the famous factor there. And in the limit of phi going to c, so the speed goes up to the speed of light, you find that term is infinite for a finite value of m0. But if m0 is in fact 0, so there's no rest mass for the photon, then this is a finite energy. But, so Heysen said that the rest mass of light is 0, and in this respect that's of course true. However, light, is always on the move at speed c. So it's just a silly argument, really. So it has no physical meaning. This bit that you all use all the time is just bullshit, really. It puts you completely on the wrong leg. You don't know what you're talking about anymore. Light is heavy. It has the mass of its energy. It has the mass of its momentum. It has the speed c. That's what you have to work with. If you put it in a box on scale, you weigh the energy of that photon. Right? So m is E over c squared. E is mc squared, m is E over c squared. Always. Always.
Not true.
Just go and wash it.
Go wash that nonsense.
Question, please.
So, certainly light does contain energy and it has inertia. We know that. So, once again, this is what we know. And we all agree on. So it turns out that this inertial mass of the light can be written like this. You can assign this mass to light. And of course, light is bent in gravitational fields and it has a gravitational mass too. There is a reaction. It's the third law of Newton. So there's a reaction force, and it can only be if the light is in fact massive. If you talk in terms of mass, this is what it is. So, and this is the mass that we exactly weigh for photons in the box. It's very important that you realize that this is really the case. So, my second part of the talk, the light clock. And so here's something about the clock. What makes a clock? Well, the clock is an oscillator, which is a resonator and a vibrating thing, whatever it is, and some energy, and a counter. So that makes a real clock. So so that in this case, in this clock, there's a pendulum, and the pendulum says tick tock. It's going like that. So that's the vibrating thing of the oscillator. And then you have a weight, and the weight puts in the energy. In this case, you put gravitational energy into that clock to make it run. It could be a battery or anything. And then, of course, there's the hands that form the counter, so that you can actually read the time. That's for a clock. Now, I'm going to go to a much more simple clock, which is the light clock. The light clock is a very special type of clock. It's just two mirrors, and you have a light pulse going up and down. And well, it is actually a resonator, so but I'll come to that. So the period of the thing is that, and you have these two mirrors that make this resonator. You have the one light pulse, which is the vibrating thing, like the pendulum, but it's also the energy of the oscillator in this case. This is the thing that can sustain by itself if there are no losses. And there are no hands to count, but you can use your own hands if you please. So, but that's for the audience to count. So, then, well, you can go. The pulse goes up and down. It goes tick tack like that, and if this is if you really use pulses, and it's very simple to make the analogy with the clock. But at some point you can make the resonator so small that it overlaps with the size of the pulse. And then you get a continuum there, it's still going up and down. A standing wave is formed, and so you get a standing wave. And you can also depict it this way. So this is also a nice way to show the density of the wave, the energy at an amplitude at a certain point. So and I will use this in a later animation, which is really nice. You will see. So that's what it means. So this is what you have in the clock, and here we have a wavelength and a half clock. You can make them any length. For convenience, you can do whatever you like. Okay. Now, what is very important to realize is that from the above, we have actually two resonance conditions on this thing. One for space and one for time. And they do not necessarily have to be the same. At some point, you have to be multiples of each other in a certain frame. But as I said, you can make this clock not a wavelength and a half, you can make 10 wavelengths, for example. So certainly these things do not have to be, there's not just one solution. And, but in the rest frame of this thing, and you can hear it coming now, indeed, this looks like a tautology, but it isn't. Now, we go to special relativity. So on the one hand, when we observe the clock from a fast moving frame, we will see time dilatation. And the clock is seen to be slowing down. This is what we also learn in school, so this is no surprise to you, I'm sure. So what you do is you have this clock, and you leave it like this, but you take your bicycle and you go very fast past it, and what you see is this thing. That's what you then see. So this thing is in the rest frame. This is when you're on your bicycle, you see this. And so you see the light bouncing up and down. And now the problem is that this length is now longer than this length. And the speed on this path is still c. Always, the speed of light is always c. So this is actually a longer path. Also, the light was going in this direction, so there is a k factor, the momentum factor of the light is here up and down. But it's here not completely up and down here, it also has a component in that direction. And now you see that if you work it out, that the period of the clock is actually slowing down. And that's because this travel light length, the light path is longer. So the resonator period of the clock increases. But we can also see that there's a Doppler effect. And there's a blue shift of the light, which is associated with the fact that there's an extra bit of k factor in that direction. So the k factor is no longer completely perpendicular in that moving frame. It has a component parallel to the motion. So if you then work that out, so that's over there, then you see what the magnitude. Can you see my mouse? No, you can't see my mouse. You can see that this is the magnitude of that parallel part that wasn't there before. Okay. Now the thing is that is a blue shift. So on the one hand, the clock period increases. On the other hand, you get a blue shift. It means that the period of the electromagnetic wave is actually getting shorter. So this seems to be in contradiction. This is a thing that Louis de Broglie recognized, and this is how he invented quantum mechanics. So, and I will argue that in a moment again. It's important to know where quantum mechanics came from. This is where it actually came from. This is the start of quantum mechanics, although you wouldn't tell immediately. Well, some of us would. So the clock frequency decreases while the light frequency increases. And as a result, we may find a beat between those two frequencies because it's still the same system. And now in this moving frame, you may actually see a beat. And this beat is then between the two frequencies that are part of the same system of a light wave in a cavity, of a standing wave of light. So, and one of the frequencies, as you see, is related to the cavity, and the other frequency is related to the wave, the vibrating thing. Okay? The resonator and the vibrating thing. Now, first I'll show you something about superposition. So if you have the sum of two cosines, and one of the frequencies is a little bit larger than the other, then this is what you get. You get a product of two. So you get something that is almost the same as the original frequency, and then you get a difference frequency, which then is like a modulation. This is a beat. In acoustics, it's also known as a little bit different in acoustics because your ear actually is non-linear in this respect, and finds here's a different frequency from what you would expect, but this is what you get. So this is the answer. You have this small difference comes as some modulation on the original frequency almost. And I'll show you that in an animation. So I hope this runs. Yeah, this runs. So it will start again in a moment. You have the two frequencies which are red and green, and they are the same, but then the green one is actually made a little bit higher in pitch, and you see what happens. So you get this modulation. This is what it does. Okay. Now, so what we do is we take our two counter-propagating waves here. So the standing wave, there it is the sum of this plus that, which gives you that in the rest frame. So you do a Lorentz transformation of the two, and what you then get is this. So what you see is that this. Sorry. Is there a problem? So I get a modulation of this thing that very much looks like the thing going up and down here, and indeed it is, because we are in looking at the transverse Doppler effect in this particular case. This is the result that we obtain. With the Lorentz transformations being written out here, so that K perpendicular, this in the moving frame remains the same, but in the parallel direction you get a little bit extra that wasn't there before, and the frequency of the thing goes up by a factor of gamma. Now we have to interpret what is there, and that will come a little bit later. So what's very important to realize is that the beat that I showed you earlier with the blue modulation. What?
10 minutes.
Only 10 minutes?
Yes.
My goodness.
Yes.
I'm halfway.
You're not the chairman.
I know, we got some.
10 minutes.
Is it?
12 minutes.
You had 22 minutes. No, you got more than that.
22 minutes sounds a lot better.
You had 20. You started at 9:08.
We have until 22.
Yeah, okay. You can rewrite this, and then you see that this is just a traveling wave here, modulated onto the original one. And so if you make a very, very long cavity, so this looks like a very narrow one, but if I make a whole gallery and have a light wave, very long, wide plane wave going up and down and up and down, then I can cycle past it. I keep on cycling past this thing, so you can really do that, in principle. Then you would see this, but you would see something extra. So you would see this going like that, but you see something extra now. And that's that. So you start to see this beat like that, also in this direction. So this is the De Broglie wavelength really. I will come to in a moment that is actually numerically also the case. This is drawn for the situation where you go at a quarter of a light speed or so. So it's very short compared to that. But what you see is that the beat is not in time, but it's actually in space. It's a spatial beat, like a Moiré pattern. And Well, that's exactly what you would expect for something like the Bohr wavelength, of course. Now, let's look at the clock as a thing that contains photons. The total energy is, of course, the number of photons times the energy of a single one, and then localized in the clock, they express their mass, m. So you have J times m, and so you get this. Well, the J is they don't matter, so you get this formula. In the rest frame, we find that this is the relationship, independent of the number of photons inside the clock, but this is the mass of a single photon. Now, what we actually see here, that you have put in this. By saying that, you do this. This is exactly the quantum condition that people always put in. This is where it comes from in quantum mechanics, always in the beginning. This is how Louis de Broglie put it in. So, you say that the energy of a photon is equal to mc squared. Which is completely justified. Certainly if you understand that light is heavy. Okay. Now for any number of photons inside the clock, the light has a wavelength equal to the quantum wavelength of this particle. Because what you saw is actually the quantum wavelength, so I have put the C here. This is just the quantum wavelength. And now you can calculate other things, and I now say that this parallel component of the wave vector is, I call it KB, and B is related to the Broglie wavelength. And I'll show that in a second. So the wavelength of that beat of the moving clock is this. So if this is the wavelength of what's inside the clock to begin with, going up and down, then this is what you have as the beat. Okay. So for a single photon clock, M0 corresponds directly to the total energy of the light inside the cavity, and then you really have, without any discussion, the Broglie wavelength. Exactly the Broglie wavelength. Not a little bit different. But of course I did this only for a transverse clock, where the light is nicely going up and down like this. Now I put it in a random orientation, and it's a little bit more difficult, but you can do it again, so you do all these things, and you have now this wave, the general wave, and you have to write this is the Lorentz transformed thing, and the minus and pluses have to do with in what direction the Lorentz transformation goes. And then this is the result. And again, you get the same thing. You get that very same beat for any direction you put that clock in, any orientation, you get this same modulation. And you get this term, which is about what's happening inside the clock. Okay. It shows that the Broglie beat is independent of the direction of motion of the light inside that clock. And of course, if you now look here, so it has here the Broglie wave vector in Z, and here it says the phase velocity times t. You could also say it's kbz, and put this there, and then here you have then the phase frequency times t. So that is your wave. What I will show in a moment, that this beat propagates at the phase velocity, and the phase velocity is c squared over v, and is a property of the internal wave in the clock. It's not getting out of the clock, it's sitting inside the clock. For the Broglie wavelength of a particle, this is different, because it's at the outside of the particle. So this is still, so you might think, oh, well, we have really got something very important here, but it's not yet very important, because it's inside the clock. Nobody can see it. So we have to do something about that. So now we go to relativistic matter. And there's our dear friend Louis de Broglie. De Broglie, I think it is properly pronounced in French.
En français.
Louis de Broglie. So, energy and momentum can be described as follows. So you have E mc squared, is this, is that is Einstein. And then for the photon, you put this. And there you go. If you then identify these two, you get this. This is again, this quantization thing. This is how quantum mechanics comes in. This is how quantum mechanics comes from special relativity. Special relativity is the source for quantum mechanics. There's no contradiction between quantum mechanics and relativity. Relativity is the mother of quantum mechanics.
By 7 years.
Yeah.
It's a long gestation.
You have to realize these things. Now you can make a little manipulation of things. So I just use that one and fill this all in, and then you can take the H bars out and stuff, and you get this. What I've done here is I've said, hey, there's my de Broglie wave vector, and I have a velocity c, and with this velocity c, I have a frequency that is this frequency. This is actually what I've done. So there's this relation. This is actually a unique relation that I just put down here like it's nothing. But it has important consequences in a moment. So I remember that one. But it makes all of this very elegant, and for the moment you can just see this as a working kind of frequency. It's a hypothetical frequency that is just easy to use. Now, of course, we have seen this. It's all in agreement with each other. Now, it's important to know this. If you have the phase velocity, this is completely general. Phase velocity is always defined as omega by k, and group velocity as d omega by dk. Now, what we see in this talk is that the speed of the light clock is the speed. We will identify with the speed of the particle and also with the speed of the group. I will just write it down of that wave. Now, from the previous, it's of course clear that this omega is the phase frequency and this k is the Broglie wave number. So, because this is also the case, we've seen that in the previous slide, then we can now calculate what the group velocity is. It's the omega by dk, you get this is what you get. So this simply comes from that. So it is one-to-one, relativity with this gives you that. So that there are no doubt where that comes from. Nothing of what I say here is invented. Sorry?
Couple of minutes.
Couple of minutes, yes.
Actually, I think we started on time. It's 9 to 9:45. It's only 9:39.
Started a few minutes late.
Started 5 minutes late.
5 minutes.
All right, so you have,
So I have 10 minutes then.
You have 10 minutes almost then.
Yeah.
Sorry.
That's
Yeah. So, now, the quantum particle has this basic wave number, kc is omega c over c. And the single external wave vector, well, that's for the quantum particle, not for the clock. Now, that's why I make this bold here. Kb, which is related to a set of not 2, but 3 frequencies and waves propagating at different velocities. So the harmony of phases, by people who know it, is about the phase and the group velocity. And so you have the same wave vector, kb times v, gives you the group frequency, kb times v phase, gives you the phase frequency. So those are the phases that are involved, and those are the speeds at which the thing runs. But there's now the third that I've introduced on the previous slide, that is this one, where the velocity c also comes in, and this is a very useful frequency to work with. What it actually means, it has to do with energy transport in the wave that goes outward, and may have consequences for the detection of particles or things. So, it is an extended form of the harmony of phases, and it just fits in beautifully. It doesn't destroy anything. It is just a thing that you can realize that it is the case. Now, so the kb is the Broglie factor. This is a thing that I have already said. So now there are a number of frequencies. So it's the frequency of the quantum mechanical wave, which is this. This is the blue shift of the thing inside. Then we have this frequency that may or not be present, but is a very nice thing to work with. That's that one. That is the beat, or the group frequency between the photon and the catalytic port. And remarkably, in the space, you get it out like kb. So that's the spatial part of it. But the frequency part of it is a numerical thing that I can write down as this. I can see that it is in time. It's the beat like this. So it's not. It's the difference. It's the beat in space. It's the difference frequency that's related to that. The frequency of the light wave and the frequency of the resonator. If you subtract them, then you get the beat frequency in time. That's a timely thing. Now, since there's a difference frequency here, you might speculate that there's also a sum frequency. If you do the sum frequency, of course, you get double the frequency. And double the frequency in the rest frame is in fact a thing that is very, that reminds us of the zeta-beweging of a spin 1/2 part.
Bring it to a close, you might be running out of time.
What's going on?
What's the question?
He has till
Yeah.
10 of now because his talk was 9 to 9:45. He started 5 minutes late, so we have till
Okay.
9:50.
I'll resign.
Yeah.
Sorry.
So you take me out of my flow here. It's not very nice. Okay. So how many phases, clock or particle? That is the thing. Well, in the rest frame of the clock cavity, the photon has a wave vector kc, while in the boost frame there appears a single extra wave vector kb, which is related not to a single wave, but to a set of wave frequencies. The phases of which are in harmony at all these three velocities. Now, how do some of these frequencies come about? From the difference between the Lorentz transformation of this wave gamma, of the light wave, and of the clock, we get this thing. Now, given that difference frequency, there may also be this some frequency. I already said this. Should figure this out. Good. Now, what's going on? Do we have superposition or do we have mixing? Because I started with a linear system with superposition. So, on the one hand, we find the spatial momentum components show linear behavior, so adding the amplitudes of waves. On the other hand, the time, the frequency or energy components show nonlinear behavior, apparently, because you have frequency mixing. So from the light clock, I find a linear superposition or additional fields give a spatial frequency beat. That's the light clock. It's a linear thing. From the quantum particle, if you just look at quantum mechanics, the time domain shows that there is a frequency mixing, a multiplication, that is, which must be due to some nonlinearity. For the light clock, the absence of this nonlinearity should be assigned to the properties of the cavity. That's the conclusion that you can draw from this. Now, in the case of the light clock, we have assumed implicitly that the cavity is infinitely rigid and massless. And we then found from the linear superposition of the waves that an internal de Broglie wavelength. But then, in case of the quantum particle, we found that for the quantum particle, external de Broglie wave also goes about as a subtraction of frequencies. Now, a subtraction of frequencies is a multiplication of waves. So that's nonlinear. Presumably, this implies.
5 minutes is fine.
Presumably, the implied nonlinearity is related to the internal binding forces, the Poincare stresses. So, a next step in our analysis of the light clock should be to include some more realistic properties for the clock cavity. I only have 5 slides left, or 4. The cavity of the light clock is actually oscillating, because if you had started with a completely rigid one, which you did, then nothing is happening outside that rigid box. But now, if we make it held together by springs, it may stretch and shrink. And this is the force of these things. And then you have the energy of the springs in there. If there's energy in the springs at some point, if you compress them or expand them, then these springs, if they are already, if they're massless to begin with, they will acquire a mass because of the energy that you put in. So you have to realize that. Okay. And over there, if the cavity is rigid, then automatically the mass is 0. If you make it non-rigid, then indeed, periodically it must have mass because there will be energy in those springs. So you can make this thing tick. So you see the photon, the light is saying tick-tack in there, and it pushes away the mirrors here. If this is a little bit floppy, and it will do nicely. And it must be similar to, in resonance frequency, to the wave inside, you hope. Now, if this thing now goes like that, then you can now see from the outside also that there is a wave inside. So you have made a coupling also to the outside world. So this is very important for the fact that we had the Broglie wavelength inside, but we actually want to have it outside as well. So this is one of the things. And of course you can now calculate what the stiffness is of this thing. And you can just put in some numbers. Now it depends on what I take for the mass of this this resonator. This is just for a mass on a string. You get this resonance frequency. So if you take something that is close to the mass of the photon in there, then you find that the expansion here is pi squared smaller actually than the whole thing. But that is just to show that it's in the same ballpark. That works. So it depends now really on whether these are springs or something else. So what is the cavity actually really made of? It's not made of silver mirrors and springs there from your wall point or so. Now, so did I guess? So by including elasticity to the clock cavity, we get the cavity and wave from a coupled oscillator. Some energy is now exchanged between the wave and the cavity and stored periodically in the binding force, which is the equivalent of the Poincare stresses. The coupling causes this to be a non-linear system with two coupled oscillators. When the clock cavity is itself oscillating, part of that wave must exist also outside of the box, because the thing is actually, you can see it from the outside. Then the Broglie wave is present both internal and external to the clock. The cavity is likely breathing itself in response to the internal light. This implies we should consider a parametric oscillator, where the impedance and light speed of the wave are oscillating themselves. A simple example would be a differential equation like this, where you have an electric field, like that, so it's the second order to T and first order. And then this is the frequency, of course, and then this is the dielectric constant. It depends on the time. Actually, it depends on E, which depends on time. Something like that. But this is not what electromagnetism looks like. Electromagnetism looks like this. In particular, if you have a topological one, where you have a little bit more with E's and B's and D's, like it is a material system. This is what you have. Those are your differential equations. Those are the couplings between E and D. So that's your epsilon R that is now going to be modulated. And in particular, you would think of a parametric oscillation where the magnetic part changes the epsilon. Now, I'm not going to go into that, of course, because I have no time. So, summary. We have shown how the Broglie wavelength of a light clock and quantum particle may have the same origin. And the roles of photon in a light clock and the nature of the clock cavity have a parallel in the wave nature of matter, its binding force and the vacuum. The questions are all the elementary particles just light in a box? Is the box perhaps some twist of space, time and vacuum induced by the presence of the light in it? The hope is to describe elementary particles with a parametric nonlinear theory of topological electromagnetism. 2 slides of conclusions. First, a Lorentz boost on any light speed standing wave produces a spatial pattern with exactly the de Broglie wavelength. The de Broglie wave is a spatial B pattern which propagates at the phase velocity. The standing wave implies the presence of a cavity. If you have a standing wave, you must have a cavity. For a rigid, massless cavity, the wave and the beat pattern are purely internal. The cavity round-trip frequency and the light wave frequency are commensurate in the cavity rest frame, but in a boosted frame, the difference is equal to the group velocity frequency. Now, from the divergent relation of the phase frequency of a relativistic quantum particle, we find the group frequency and the de Broglie wave again. Those are external to the particle. The quantum wave corresponds to the internal light speed of wave and is a consequence of the energy quantum condition of the quantum particle. Now, for the stability of both the clock cavity or the quantum particle, some internal forces are required. The famous Poincare stresses again. We know that. Nobody knows what they really are. For a non-rigid cavity, energy is exchanged between the wave and the springs, and thus they form a coupled oscillator. And for a cavity boundary that's itself oscillating, presumably that the Broglie wave exists in the whole of space. And you can ask questions about that. The quantum particle may be mimicked best by a light clock with a cavity that is in fact a parametric oscillator. This would mean, in some sense, that the light is waving in the vacuum and the vacuum is waving in the light. And if you go back to the 1997 paper by John and me, you find this is an artist's impression of spinning briefer. And you see that the thing goes round with the double frequency, but if you see how what it does radially, it is just the omega c. And this would produce exactly the Broglie wavelength, while it still has a zeta wave of the double frequency, which is nice.
Good to get that, Martin. Good to get that.
Yes, it's finished. Just let me finish.
The bosses are over there.
Thank you.
Thank you.
I would have finished 2 minutes earlier if you would not have interfered.
Still have been over time. Is it time for a couple of questions?
No, questions during the coffee break. We're over time.
Yeah. But thank you. Thanks so much for that.
Thank you, as well.
So lovely. Glad to set up.